Hello, Vanakkam. Welcome to the Electrical Engineering Examples channel. In this channel, I will focus on example problems with detailed solutions. And the whole idea is to help you maximize your exam performance. In this video, we will be looking at impedance transformation for a three-phase transformer-based system. Here is a question: a balanced delta connected resistive load of 8,000 kilowatts, so it's 8 megawatts basically, is connected to the low voltage delta connected side of a Y delta transformer rated 10,000 kVA, 10 MVA basically, comma 138 per 13.8 kilovolts rating. Okay, so let me reread the statement and extract the important information. So if there is a balanced delta connected resistive load and the three-phase power consumed by this resistive load is 8,000 kilowatts, and this resistive load is connected to a low voltage side of a Y delta transformer, and the delta side forms the low voltage side of the transformer. Okay, and the transformer is rated for 10,000 kVA, which is the three-phase power rating, and the line-to-line voltages on the high voltage side or the Y side is 138 kV, and the delta connected side is 13.8 kV. So the voltages are always line-to-line quantities because only line quantities are accessible, and the power for a three-phase system is always three-phase power. Okay. With that information, let us proceed. If the load is supplied at rated secondary voltage, that means the voltage across the delta connected load is 13.8 kV, find the load resistance in ohms. Okay, so the value of load resistance in ohms in each phase. So basically it's a per phase load resistance value that needs to be found as measured from line to neutral on the high voltage side of the transformer. So basically the load is connected to the low voltage side as per the problem statement. We need to calculate the value of load resistance when it is referred to the high voltage side of the transformer. And one important point that is specified here is neglect transformer impedance. So the transformer impedance can be ignored. This is the first part of the question. There is another small question which asks, will the answer change if the transformer is Y connected instead of Y delta connected? If everything else remains the same and if just the transformer connection is made into YY, will the load resistance value referred to the high voltage side change is the question. We will answer the second part later, but let us first try to solve for the load resistance value when it is referred onto the high voltage side of this setup. As always, the first step that one needs to do in such a problem is to sketch a schematic diagram representing the system. Okay. So recollecting the question, there is a Y delta transformer. So I will have Y connection on one side, and there is a core which is represented by these two parallel lines, and then there is a delta connection on the other side. This delta connected side is the low voltage side, which is rated for 13.8 kV, and the high voltage side is rated for 138 kV. Okay, that is specified in the problem statement. And to the delta connected side of the transformer is the load that is connected here, and the load is a purely resistive load, and that is also delta connected. Okay. So the load, let me call each of the resistors in each of the phases as R subscript L. Okay. Because it's a balanced load, they will all be equal in values. And the total power consumed by this three-phase load is specified as P3 phase, or the load end is specified as 8,000 kilowatts. Okay. One more statement was indicated saying that the voltage across the load is nothing but the rated secondary voltage, which is 13.8 kilovolts. Please note, these are all line-to-line quantities. The line-to-line voltage across the load is 13.8 kilovolts as per the problem statement. Okay. Of course, the transformer will have its own primary connected to a source somewhere, which we are not bothered about at this point in time. What we want is to calculate the per phase resistance value, the load resistance value, when it is referred onto the high voltage side. So when I transfer, or when I transform this per phase load resistance from the low voltage side onto the high voltage side, I would like to know the value of this resistance. Okay, that is what the problem statement asks. So this is the first step. We will always sketch the schematic. The transformer is placed inside an enclosure. So only these points that are outside of the green box are accessible. Anything inside the green box is not accessible. Okay, so what we have access to are the terminals, which will always be line to line quantities. That is what I want you to keep in mind. And because the high voltage and low voltage side are known, we will label these sides appropriately as A. Uppercase stands for high voltage and lowercase stands for low voltage. And at the load side, we can call these as A, B, C themselves. Okay. Now the next step, so this is the first step. We have drawn the schematic, and this transformer is rated for 10,000 kVA three-phase power. This is the rating of the transformer. This is what the transformer can safely deliver as per the manufacturer. And right now, since it's only supplying 8,000 kilowatts, which is below 10,000 kVA rating, there is no problem. Okay, the transformer is not overloaded. It's not even supplying rated power. Okay, that is the first thing we understand. Okay, so now we will move on to step 2. Step 2 is using the information specified. Let us first determine the load resistance value in each phase of the delta connected system using the values specified in the problem. Let us determine the value of RL. What is RL? As per the diagram, RL is the per phase load resistance value in the delta connected setup. Okay? RL is the resistance, load resistance in each phase of the delta connected setup. And in order to calculate RL, we first have to determine the per phase power consumed by the load. So per phase power consumed by the load is nothing but 8,000 kilowatts divided by 3. Okay. Now per phase voltage across the load resistor RL is same as the line to line voltage because the load is delta connected. Very important. Because the load is delta connected, the line to line voltage will be same as the phase voltage, and consequently the per phase voltage across the load resistor is 13.8 kV. Now once we know the voltage across the resistor and the power consumed by that resistor, we can calculate the value of RL as V per phase square divided by P single phase, which is 13.8 into 10 power 3 into 13.8 into 10 power 3, that's what square means, divided by 8,000 into 10 power 3 divided by 3, which is the single phase power. And if I do the math, let me use my calculator here quickly. 13.8 K into 13.8 K divided by 8,000 K divided by 3. If I do that, I get a value of 71.415 ohms. So what I'm going to do is I'm going to go backwards in my slide and I'm going to indicate RL is equal to 71.415 ohms from next slide. Okay, so as per the calculations that I did on the next slide, I found the value of RL, which is the balanced resistance per phase of the delta connected load, to be 71.415 ohms. Now this is step 2. So we have calculated RL. Step 3 is going to be the conversion. And since there is a delta connected secondary side of the transformer and delta connected load, we have to convert all the delta into equivalent stars. Converting all the delta into equivalent connections. So the first, on the high voltage side, which is already Y connected, there will be no change. So there will be no change on the 138 kV side. This will remain intact. So the 138 kV is the line to line voltage. On the high voltage side, that will remain intact. Then I am drawing the core of the transformer using two parallel lines. The delta has now become an equivalent star. So I'm going to use a different color just to indicate that this is an equivalent Y. Okay. Actually, there was a delta here between these points. Okay. There was a delta, but I converted the delta into equivalent y. Now, the moment I convert delta into equivalent y, that I can make this all blue so that it is easy for us to keep in mind. Just the delta is converted into equivalent y. The line-to-line voltages will still remain the same. And that is what an equivalent system should be, right? When I convert delta into y, the line-to-line voltage or the line current should not change. It's only the fictitious changes are happening inside. So what will now happen is the phase voltage of this, because of this equivalent y, okay, there will be a neutral point, and the phase voltage will be 13.8 kV divided by root 3. This will be the phase voltage of this imaginary or the equivalent y connection. Why is that? Because the line-to-line voltage cannot change. It is still the same as 13.8 kV. So if I convert a delta into an equivalent y, the equivalent y's phase voltage will be 13.8 over root 3 kV. Okay. And then there is a delta connected load which has to be converted into an equivalent star. So I'm going to do that as well. So I'm going to okay. Now, what will be the new value here for the resistors? If you do a delta to Y conversion, the value of resistance or the impedance will get modified. So now RL Y, which will be, let me call this as RL dash, or no, let me not call this as RL dash, let me call this as RL1. Okay. These are new values. In fact, let me call this as RLY itself, just for the sake of consistency. So these are the Y equivalent resistors of the original delta connected system. The original system was delta connected. Okay. We have now replaced the original system mathematically using its equivalent Y connection. So the values of resistors will be modified, and RLY will be, by definition, R delta or RL delta divided by 3. Okay. So the value of RL Y connection will be the value of RL delta, which is 71.415 divided by 3 ohms, which is nothing but 28 something, 23.805 ohms mega. Okay, so this is the resistance of the load when it is converted into an equivalent Y connection. Now that we have converted all the delta connections into equivalent Y, we can redraw this three-phase diagram into a single-phase equivalent. Before that, let me quickly draw the phase voltage on the high voltage side as well, just for our sake. So the phase voltage that exists on the high voltage side is 138 divided by root 3 kV, because the high voltage winding is Y connected. Okay. Now, once we have got all these things, the phase voltages are all the same on the secondary side. On the primary side, it's 138 kV by root 3. So let us go ahead to step 4 and draw the per phase equivalent circuit. Of the system on the per phase representation. So if I just consider one phase, I will have my high voltage winding, the voltage of this will be 138 divided by root 3 kV. So this is the HV side, and then I have my core, and then I will have my equivalent Y, which is red in color. This voltage will be 13.8 over root 3 kV, and then this is now connected across an equivalent load resistor, which is 23.805 ohms. Okay. So what is the turns ratio of this single phase transformer? It is nothing but 138 divided by root 3 is to 13.8 divided by root 3, which is nothing but 10:1. So the turns ratio of this single phase transformer is 10:1. And all I want to do is I want to bring this load resistance onto the high voltage side. So the high voltage side, or when the load resistance is transformed to the high voltage side, so the last step, step 5, is transfer the load resistance per phase. So per phase load resistance to the HV side. And that can be done easily. We know the equation. It is nothing but RL dash per phase is equal to N1 over N2, the square of it, into the actual value of RL, which implies it will be 10 square over 1, which is 100 into 23.805 ohms, which is 2380.5 ohms. So the per phase load resistance, when referred on to the high voltage side of this transformer, is going to be 2380.5 ohms. Okay. Now there is one intuitive way to say whether this makes sense or not. Always the resistance on the low voltage side should be smaller in magnitude than the resistance on the high voltage side. The reason being, on the low voltage side, the amplitude of current is higher than the amplitude of current on the high voltage side. And therefore, in order for the transformer to maintain power balance, I square R loss on both sides should be equal, okay, for an ideal transformer. And for that to happen, the resistance on the low voltage side, where the current is going to be larger, has to be smaller in value compared to the resistance on the HV side, where the current is going to be smaller. So by comparing the LV side value of 23 ohms to HV side value of 2380 ohms, I can intuitively say this makes sense, that when I transfer resistance from an LV side onto a HV side, its resistance increases, which makes sense. Okay, so this is one easy way to intuitively check whenever you come up with some numbers. So this solves the first part of the question, which is to identify the load resistance when transferred onto the HV side of the winding. Now, what happens if we change the connection type? So this is part B. Part 2. When the transformer connection is changed to YY, what will happen? So let us go back to step 1 and let us redraw the schematic. So the schematic will be something like this. We have a high voltage side which is already Y connected, and this voltage level is 138 kilovolts line to line. Always the value specified in the problem or line to line for a three-phase system. If it is a single phase transformer, then there is no concept of line to line. It is only phase to neutral that will be accessible. And then the secondary side is also Y connected as per the new problem statement. And the line to line voltage is still the rated value of 13.8 kV. Okay. And there will be a delta connected load whose value is now known to us because it's the same load from the previous part. And this will be 71.415 ohms each. And that will consume 8,000 kilowatts of power when subjected to 13.8 kV. Okay, so this is the HV side, this is the LV side, this is the new schematic diagram. The step 2 is going to be eliminated because we already know the value of resistors from previous part. So now we will jump on to step 3, which is convert all the delta into star. There is only one delta, which is the load side. If we convert it into equivalent star, so the next step, let us say step 2, in this case, is converting delta to star. So we will have our transformer primary, which is Y connected. Secondary is also Y connected. The load, which was originally delta connected, is now converted into an equivalent Y with a new value of resistors. And these values are also found in the previous part, so we will not do the math, but you will note that these are 23.805 ohms each. Okay. And the voltage that is appearing across the load side line to line is 13.8 kilovolts. This is the line to line voltage. The voltage appearing across the transformer primary will be 138 kV. Okay. So the per phase voltages of the transformer primary is going to be 138 divided by root 3 kV. And on the secondary side, the phase voltage across the transformer is going to be 13.8 divided by root 3 kV. So the turns ratio of this transformer has to be considered or calculated using the per phase voltage ratios, not the three phase voltage ratios, but per phase voltage ratios. And we see that when we have a YY connection too, if we look at only the single phase part of the new circuit, so let us quickly draw the single phase representation. Draw the per phase schematic. We will get there is one winding with 138 divided by root 3 kV as the voltage, and on the other side we have 13.8 kV divided by root 3 as the secondary side voltage. This is HV, this is LV, okay. And then we have the load, which is 23.805 ohms. So the turns ratio is once again found to be 10:1, interestingly. So this is once again a 10:1 transformer. So if we transfer the impedance the load resistance value RL prime will be 2380.5 ohms, which is exactly the same as what we obtained in the previous case. Okay. So what we can conclude from this example problem is that irrespective of the three-phase transformers connection type, the turns ratio remains the same. And incidentally, or we observe that the turns ratio can be easily obtained using the line-to-line voltages themselves. What this means is, when we have a three-phase transformer, whether the connection of the transformer is YY, Y delta, delta Y, or delta delta, as long as we know the line-to-line voltages of the transformer, then the turns ratio of the transformer can be obtained by simply taking the ratio of these line-to-line voltages. This makes life very, very convenient. Okay? And because the transformer's turns ratio remains the same irrespective of the connection type, when we transfer an impedance from one side to another side, irrespective of the connection type, the impedance transformation will remain the same. And it is because of this reason, whenever we want to solve a problem in future for a transformer circuit, and if the impedance, the equivalent impedance of the transformer is known ahead of time, we don't have to really do all the delta to Y conversions. We can directly replace the transformer with its equivalent impedance, because we know, irrespective of the connection type, the equivalent impedance of the transformer on a per phase basis is going to remain the same. And that is the important learning from this example problem. So in future, if there is a problem that has the impedance of the transformer specified, when I say this, what I mean is I mean the equivalent per phase impedance. So we can completely replace the transformer without worrying about the connection type with its equivalent impedance. If there is a problem that has the impedance of the transformer specified, then without bothering about the connection, of the transformer, its equivalent impedance can be used. This is an important learning, because in future, whenever we are solving problems using transformer circuits, if the equivalent impedance of the transformer is known, then we don't have to bother about the delta to Y conversions. We will just replace the transformer as a whole using its equivalent impedance on its per phase diagram. So the only thing we will then be worried about is the load, whether the load is delta connected or Y connected. If the load is Y connected, or if it is assumed to be Y connected, then constructing the per phase diagram is very, very simple. Okay, so with this learning, I will end this problem here, and I will meet you again in another example problem video. Thank you so much.